So Chebychev's inequality has the following corollary for estimators. Okay, and so this corollary relates Chebychev's inequality to confidence intervals. Okay, so suppose you have t, which is an estimator for a parameter theta, and suppose it has a mean squared error of gamma, and we are assuming that there is you know this gamma for now. Okay, as you will see, there are lots of cases where we have some a priori, in some sense, trivial estimate for what gamma should be. Maybe because this random variable is somehow bounded or something like that. And then what we would like to claim is that if you have any alpha more than 0, then setting L to be equal to t minus square root of gamma by alpha and u equals t plus root of alpha by gamma, that gives you a valid alpha confidence interval. Okay. So if you remember, confidence intervals were parameterized by this alpha, right? So what this is equivalent to saying is that probability that theta belongs to this interval, which is t minus root of gamma by alpha and t plus root of gamma by alpha, this is more than or equal to 1 minus alpha. So this was the definition of alpha confidence interval, right? So we have this is L, this is U, and these are two statistics because t is some estimator which is also a statistic, and you know gamma and you know alpha. Okay. So this is what we would like to claim, right? And this is actually true for a fairly simple reason. So suppose we set, just to see the simplicity, to see the equivalence, suppose we set C equals 1 by or root of 1 by alpha. Okay, then this one is the same as probability that theta minus t is less than or equal to C root alpha. Right? Why is that? Because I succinctly wrote this as probability that t minus theta absolute value is less than or equal to root of gamma by alpha, because that's the same thing. Oh, sorry, this should be gamma. Okay, so these two are equivalent. Okay, and now what is the probability? What is this probability, right? So this one is, so it's saying what is the probability that theta minus t is less than or equal to C root gamma. Okay. It's very tempting to use Chebychev's inequality here, but note that Chebychev's inequality says that probability that theta minus t is more than C root gamma is less than or equal to one by C squared. So this would be C less than or equal to 1 by C squared. Okay, and 1 by C squared, because C is like this is exactly equal to alpha. Okay, so the probability that theta minus t is more than this is less than or equal to alpha. Therefore the complement, therefore probability that theta minus t is less than C root gamma must be at least 1 minus alpha. Okay, so if you think of alpha as being 0.1 or something, then Chebyshev is telling you that the probability that this quantity t minus theta is more than C root gamma is less than 10%. Okay, so is less than 0.1. Therefore the probability that this is smaller than that must be more than or equal to 0.9, right? Because these two are complementary events. Okay, and note that this is exactly what we want, right? So So that's the quantity that we're interested in. There is this mild technicality of less than or equal to versus less than, but note that this is only stronger. If the probability that theta minus t is strictly less than c root gamma is large, then the probability that theta minus t is less than or equal to c root gamma is also large. Okay. So this is a strictly stronger quantity than that. Okay. So this is why if you have a bound on the mean squared error, then you automatically get a confidence interval. Okay. So there's one simple observation that we will make from here. This observation is that if alpha drops, so if alpha is small, if we want a high confidence, that is tiny alpha, then the width of this confidence interval increases. Okay, by width I mean the gap between L and U. Okay, and this is easy to see, right? So what this is saying is that suppose I have I have the value of the estimator, let's say it is t, and suppose I want firstly alpha equals some value, so let's just set alpha being 0.04. Let's assume that we know that gamma equals 1. Okay, so mean squared error is smaller than equal to gamma. Then what this is telling us is that, so t has some distribution. Let's say it looks like this. And now if we look at t minus square root of alpha is like 0.2, that's why I chose this thing. T minus root of 1 by 0.04 and t plus root of 1 by 0.04. So what is that equivalent to? That's equivalent to, if you think about it, this will be t minus 5 and t plus 5. Okay, and this is telling us that this probability is smaller than or equal to 0.04. Okay, and note that if I want to replace this 0.04 by, say we want to replace 0.04 by 0.01, okay, that means alpha is smaller, then what Chebychev's inequality will tell us is that if you want such a guarantee, then you've got to, your intervals are now like the L nu is equal to 1 by 0.01. Okay, and this is equal to t minus 10. Okay, and L old used to be t minus 5, right? So and same with u nu, t plus 10. So so the interval now gets larger. Now if you want a much higher probability, then it's you are saying that, oh, okay, if I want 0.01 probability of failure or 99% confidence, then I can only say that this theta lies between t minus 10 and t plus 10. Okay? And this makes intuitive sense, right? Like if I want to give you an interval in which theta lies, okay, and then if you have a much smaller interval, then you must have a lower confidence that theta must lie, because the number of samples is staying the same. Okay, so t was an estimator that was using some n samples, right? and let's say n was something, so n was like 10 samples. Using like 10 samples, there is some bound to how confident you can be that that a parameter is within some interval, right? So, and if you want a high confidence, just using these n samples, then your width of the interval, it makes sense that it grows, okay, and and that's exactly the kind of trade-off that we are seeing because of this root alpha coming in the denominator. Okay. So it turns out that in many cases, the dependence is not as bad as root alpha. Okay, and that's something that we will focus on in the next, like a few minutes from now. Okay. Alright, so first I wanted to apply this to this very simple case of the Bernoulli distribution. Okay, so the application to estimating P in Bernoulli of P. So this turns out to be a very simple application, and because one nice thing about the Bernoulli is that it takes value 0 or 1. Okay, so it takes value 0 with probability 1 minus p, takes value 1 with probability p. Okay, so the mean squared error, we have a trivial bound on the mean squared error, is always less than or equal to 1. Okay, as long as your estimator, okay, as long as estimator produces a value between 0 and 1. Okay, so if as long as the estimator is somewhere over here, produce a value out here, and it's guaranteed to produce a value somewhere over here, you know that the mean squared error is smaller than 1, right? Because always the gap between the estimator and the value of the actual value theta will be smaller than equal to 1. Okay, so this is one simple setting where we actually have a very simple bound on gamma. Okay, so let's now use this. Okay, so suppose we consider the estimator that we had before. Okay, so the sample consists of n elements, let's say, to xn, and t was simply x1 plus x2 up to xn divided by n. Okay, we saw last time that this is an unbiased estimator for p. Okay, so if you have this quantity, let's now see what Chebychev's inequality gives us about the confidence interval, right? So one thing that we saw last time, which is the mean squared error of this estimator. Try to look at last week's notes of last class's notes. So this is actually less than or equal to, or in fact it was exactly equal to p times 1 minus p divided by n. Okay, and this is always less than or equal to 1 by n, right? Because in fact it's less than or equal to 1 by 4n, right? Because we know that p times 1 minus p is always less than or equal to 1/4 for any p in 0, 1. Okay, so we know that the mean squared error of, if you use n samples, is less than or equal to 1 by 4n. Okay, now let's try to use this to get bounds on the confidence interval.